trying to do in this Systems That Learn initiative. So I'll start off with a sort of general high-level motivation about our objectives in the project and why we think this is an important thing to do. And then I'll talk just briefly about a couple of technical projects that we're sort of taking on under the auspices of the Systems That Learn initiative. So I guess you guys are here, so you all know that machine learning is eating the world. It's taking over, it's been tremendously successful in some domains, right? If you look at things like image processing, we now have these algorithms that can do things that you just never thought would be possible before. These deep learning algorithms have just transformed our ability to use computers to recognize and understand images. And we're seeing some similar benefits in areas like speech processing and natural language understanding. And so that's led to, I think a belief that the next decade of computing is essentially going to focus on how we can use these algorithms to transform many of the sort of human activities that we engage in every day. How can we use computers to perform these human-like tasks to augment how people act in these very complicated real-world settings? And so these are applications like personalized medicine, like building better conversational systems that will go beyond the sort of Siri and Alexa and into driving online tech support, driving a lot of tasks that are now accomplished by humans. Moving towards autonomous vehicles, where we're going to have software systems that are helping us drive or driving for us, to robots that we're going to be interacting with in a much more kind of personal way, as opposed to robots simply for manufacturing. So I think we're all aware of this. This is coming. It's clearly going to continue to consume technology for the next decade, and I think it's going to have huge impacts on our society. And many people are, of course, talking about some of the social implications of these technologies. I want to talk a little bit today about some of the technological challenges with putting these machine learning algorithms into practice to sort of motivate what we're trying to do with the Systems That Learn initiative. Okay, so why is this happening now? I guess that's a natural question to ask. It's happening, I think, really for three reasons. I mean, the first one is, of course, the flood of data that we now have available. So that sort of what big data meant was, everybody invested a ton of money into collecting data about everything. We suddenly have smartphones and other sensors everywhere in our homes, in our cars, in our pockets, and we have just an immense amount of information. The second thing that's happened is these methodological advances. So deep learning as well as other machine learning algorithms that have really gotten to the point where they're actually quite remarkably sophisticated, very, very good at performing tasks at levels that are competitive with humans, right? So we're starting to see these algorithms that can, for example, recognize things in pictures or process a video when you're looking out the front of the car in a way that's, in some cases, better than the human perceptual system, which is pretty remarkable. And then, of course, this is coupled with just this massive rise in computing power, these massive scale heterogeneous hardware clusters, ubiquitous network connectivity, the ability to have everything connected all the time, and these very large data centers built by companies like Amazon and Google, the sort of rise of cloud computing, which now means that everybody can have access to this really massive scale computing. Okay, so our goal in Systems That Learn is to, essentially we say to accelerate the development of Systems That Learn. So what is a system that learns? Well, it's a system like an autonomous vehicle, right? It's a system like a personalized medical assistant, something that can give you advice about some medical diagnosis or customize a medical diagnosis for you. And building these systems is going to require a really complicated mix of algorithms as well as sort of sort of software engineering know-how, if you will. Like, how do we build these large-scale, massive systems that continue to evolve over time, that can run on thousands of computers, that can be distributed across little phones and large-scale software systems. So we have to take these kind of two groups of people, the people who develop the algorithms, the machine learning, and the people who know how to develop these massive scale software systems. We somehow have to get them talking to each other. And that's really what we're at from a sort of organizational perspective inside of a place like MIT, where these two groups are sort of like oil and water, we're trying to bring them together to sort of, so it's more like this, right? So we want them to, these two people to be, these two groups to really come together and work together to solve what are these really hard problems. Okay, so why is this going to be an important thing to do? Well, so first of all, I think you guys, many of you are probably aware that the practice of machine learning, despite these massive advances, is still largely a black art, right? If you look at how the people who've been successfully able to deploy these machine learning algorithms, they're typically very large teams of multiple PhDs who are, developing these algorithms. These are not yet at the point where a, typical software engineer can just pick up these algorithms and do something with them. And furthermore, even when these algorithms work, it's often hard to understand why they work. Okay, so this poses a real challenge if you're somebody who has a business and you say, well, maybe I can use machine learning to solve this problem. If you can't understand why the algorithm is going to work, or when it's going to work, or when it's going to fail, then you're going to be very cautious about putting these things into practice, right? And I think that's a lot of the hesitancy that when you talk to people who are skeptical about self-driving cars, for example, that's one of the challenges, right? Is that, yes, it seems like these algorithms can work really well under a wide array of situations, but I think people are going to naturally be very cautious about allowing a car to drive for them 100% of the time, unless this algorithm is just really, really, really good, and they can understand when the algorithm is going to work well and when it's not going to work well, right? If it just randomly fails 1% of the time, that's not going to be acceptable to people, right? And worse, it's hard to sort of understand how to maintain and evolve these machine learning systems. It's not, we have good practice for software engineering, but we don't really have good practice for machine learning model engineering. And I'll talk about that a little bit in one of the research projects in a minute. And this is complicated by the fact that inside of organizations, that there are different teams that typically do the development and deployment of these systems, but there are people who develop the machine learning algorithms and models, and then there are people who implement them, and they're typically separated from each other instead of being together, the same people, and that makes it very difficult to adapt and evolve these models over time, for example, as you get new data that feeds it. So this has led to some really noteworthy failures. I'll give you and some cases where these algorithms behave in very unexpected ways. So I'm going to give you a couple examples of that, and I'll talk a little bit about some of the things that we're doing to make it better. So I guess some of you probably heard the Microsoft Pay chatbot failure. So this was in the press last year, I guess. So this is this chatbot that, well, let me start off by saying a little bit about what the chatbot was designed to do. The chatbot was developed by Microsoft. The stated goal of this thing was to respond to tweets on Twitter that were sent to it in a way that was supposed to be reminiscent of a teenage girl. Okay, so whatever that means, it was supposed to have a teenage girl persona. Okay, and so they trained it on some data, presumably, and put it out there. And the idea was that it was supposed to be conversational. So it would engage in conversations with you about whatever topic you wanted to talk about, which naturally meant that it was sort of a system that learned. It learned from what you said and sort of parroted things back to you. The problem was that people realized that this thing was learning from what they said to it, and they trained it to say some kind of offensive things like, we're going to build a wall and Mexico's going to pay for it, which seemed funnier like 6 months ago. And many worse things like Hitler did nothing wrong, terrible slurs and really offensive, incredibly offensive things. Okay, so they basically got they trained this chatbot to just behave in a completely unintended and unexpected way. It's kind of embarrassing, I think, to the researchers who did it, because, you could say it was an interesting sociological experiment, but my perspective is it's kind of embarrassing. These were people who, ostensibly were the experts in the world who trained, this is Microsoft. They have a huge team of researchers who, are supposedly the experts in this machine learning technology, and they put this thing out there, and, it behaves in this very unexpected and kind of unintended way. Okay, here's another example. Can anybody spot the difference between these two pictures? You're not supposed to be able to spot the difference. I'll show you the difference. If you were to take the pixel by pixel differences, that's what you would see. So it almost looks like nothing, okay? It turns out that if you train a deep network to recognize these two pictures, so these researchers in this paper, what they did is they took one of these deep net image image recognition algorithms, okay? And they essentially developed a way to transform inputs in it to fool the network, to make it believe that it was seeing something that it wasn't, okay? So when you ask this network to identify the picture on the left, it correctly identifies it as a poodle, okay? When you change just these pixels here, which a person can't see at all, what the network identifies this thing as an ostrich. Okay? And in fact, what they showed is that they could make this thing with, with what their algorithm does is it finds a minimal set of pixels that you can change in the image on the left to make it into anything you want on the right. Okay, so they could have made this thing say this was a bulldozer or a rat or whatever they wanted. Okay? They could have come up with made it look like, they made the algorithm believe it was seeing any animal you wanted. And yet to a person, these things look exactly the same. Okay, so what sort of, so we see all these results. Sometimes you see these results from these deep learning systems that make you believe that they're perceiving things that are sort of the way that people perceive things. But yet, when you see an example like this, it's very clear that this algorithm is not perceiving in the same way that you or I would perceive. It's looking at something else in these images, and that's what it's queuing into when it learns what it's giving out. And this is a little bit worrisome because it's hard for us as people who want to apply these algorithms to understand when the algorithms are going to fail. If I can't understand why it said this was an ostrich, it's hard for me to have a lot of confidence if I want to put this algorithm into production on some website, right? Okay, so these systems, what I sort of have been talking about so far is systems that learn in the sense of like large-scale human systems. So these systems like self-driving cars or medical or medicine or online chatbots. Okay, these are large-scale systems, but there is a sort of another meaning of systems, which I think we're also trying to address here, which is that computers themselves, oftentimes we talk about computer systems like operating systems or the internet. We would call those systems as well. And actually, I think there's one of the things that we're very excited about is understanding how we can use these algorithms themselves to actually optimize the operations of these large-scale software systems. So, one example of a cool thing that some researchers at MIT have done recently is that they've taken the TCP protocol, which is the thing that controls how packets are transmitted on the internet, and they've actually shown that you can use machine learning algorithms to optimize the TCP protocol for whatever environment you're running in, and you can do better than any human could hand-tune this protocol. So it's this very kind of cool way that you can get better performance out of a system like the internet by optimizing it with machine learning. Okay, and so that's definitely one of the objectives of this research project as well. Okay, so the overall sort of goal with systems that learn basically is to we say accelerate the development, deployment, and evolution of large-scale software systems that incorporate machine learning and artificial intelligence. And so I'm not going to go into too much more of the sort of details of what we're doing in systems that learn. And if you're interested in learning more about it, of course, we would, we're looking for new members. We'd love to have you join. But what I thought I would do with the rest of the time that I have, the next 15 minutes or so, is to just talk about a couple of ongoing projects that I think are cool that fit under the umbrella of systems that learn. Before I do that, maybe does anybody want to ask questions, like maybe about my examples or something? Yeah.
So, question with machine learning in cars. Is there a threat that they'll pick up bad habits of drivers, where the training data is the anti-bad coming?
Well, I think that's a complicated question that you could talk for a long time about. So, right now, most of what's happening in machine learning in cars is that we're training models offline and then deploying offline training models. There are people who are talking about how awesome it would be if cars could learn from each other, which in one way would be awesome, but it also does open up the question of whether cars could start to, do you want to have that kind of online learning happening? Because then, somebody might be able to cause cars to learn some really terrible behavior. I personally think that there's one very interesting question around training these cars and whether we're training them, we're sort of training these cars in most of the training of cars is, it's training these cars to be able to avoid, drive in a way that avoids getting in accidents, right? But you see some of these examples if you poke around online of these cars behave sometimes in ways that are very unintuitive to humans or not the way necessarily a human would drive. So, apparently a sport in Mountain View is to go find the Google self-driving cars and do funny things in front of them so that they can't drive down the road anymore because they won't, they see certain gestures that people are making and they think about to jump out in front of them or something. Okay, so you know, how do you train cars that actually behave more like the way that a person would behave? I think is a really interesting question, but it's a very nuanced and complicated question. So, yeah.
If I understood you correctly, a moment ago you said, if you're interested, you can join us.
Yeah, so this is I didn't say anything about this. So it depends on, I don't know who you are, where you're coming from, but if, you know, for people who are coming here, who are coming from a company, you know, who might be interested in participating in this project, this is an industry-backed initiative, and the idea in this initiative is that we bring in companies who are, you know, interested in the same kinds of problems to work with our researchers and help us kind of, first of all, understand the research we're doing and also influence the research we're doing. And so we would love to, you know, have people come and have people from industry come and be a part of this. If you're not from industry, if you're from academia, then, you know, certainly get on mailing list. We have events going on. Come, you know, hang out and see what we're doing and talk to us, and we're always excited about that. So, yeah.
Based on your experience, do you see a place where computers actually make all the decisions, or are people gonna, or you know, we're far away from that, we can't even see that? Because there's actually a quote from Albert Einstein that was super interesting. It says, computers are incredibly fast, accurate, and stupid. Humans are incredibly slow, inaccurate, and brilliant. Together they are powerful beyond imagination. And so I'm wondering what your thoughts are on that.
Yeah, so the question is, you know, are we ever going to see a situation where cars are making, or where software systems, machine learning algorithms are making sort of, I would characterize it as closed loop decisions without a human sort of sitting there, you know, looking over over our shoulders at every moment. And I think, I mean, clearly this self-driving car thing is about that. I mean, the people who are advocating self-driving cars in the most extreme view of it are saying, we're just going to give up control over the car to, an algorithm, because the car, they believe the car is going to be able to do this in a way that is safer and more efficient than any human can do it. You know, I think the jury is out as to whether people are going to accept that this is really possible. You know, we already see this in, you know, there are other limited domains where, of course, algorithms are already making closed-loop decisions, like deciding what ad to show to a person on the website. But showing what ad to show to a person on the website is a very low-risk thing to do. The question is, you know, driving is a much higher-risk thing to do, and there are even riskier things that you might be tempted to deploy algorithms to run, like, you know, algorithms to control our, power plants, or algorithms to control the internet, for example, right? I mean, if you know, the internet is a collection, there are humans who essentially control how data moves through the internet, and right now those are people who are inside of big companies who their job is to make sure that all the configuration of the routers and the internet is done properly. But you could imagine that algorithms could do a better job of this. But when you start giving closed loop control to algorithms, you know, you introduce the potential for all these kinds of risks. So I mean, I think this is not an easy question to answer. It's not something where, you know, one person is going to have the right answer, and every industry that starts to adopt these technologies is going to have to think about how they adopt them carefully in a way that doesn't expose them to some of these risks and failures. All right, I have some more things to say, so I'll say a few more things, and then I can take some more questions at the end. All right, so we've got a lot of stuff. I mean, this is, as Lori said, there's, you know, 50 plus research groups at CSAIL. Some 30 of them are sort of, 20 to 30 of them are nominally a part of our systems that learn initiatives. We've got stuff that's going on in programming abstractions for machine learning, maintenance, management, and monitoring of these algorithms as they're deployed, infrastructure for integrating this train, deploy, run cycle, giving the algorithms that have performance guarantees, giving algorithms that have safeguards, building algorithms that learn in private, you know, that can learn without exposing the information that they're trained on, algorithms that can provide certain kinds of security guarantees. So there's a ton of stuff going on, and it's really around this acceleration and democratization of systems of learning. And you know, the other part of it that I think is really important personally is that, you know, it's about training people to think differently. Like right now, we train people to think about being good engineers, or maybe we train people to think about being good modelers, but we're not doing a great job at places like MIT of training people to be good at doing both, and we kind of need to do that. All right, so with that high level thing said, I want to talk about just quickly about 2 research projects. So this first research project is from 2 of our PIs, Rebecca Barzilay and Tommy Yakala and some of their students. So they work in the area of natural language processing, and natural language processing is one of these areas where machine learning has, and especially deep networks, have started to really transform the field. So we have these algorithms that, when they're trained on natural language, can learn pretty remarkable things. So for example, they have this is an example of a network that they built. They call this multi-aspect review analysis. Okay, so this is, you want an algorithm that can take a piece of text and can give you some multi-aspect rating of that text. So in this particular case, this is an algorithm that's rating a restaurant review with a star rating. But you can imagine why you might want this in, customer support, or triaging of some kinds of requests, or maybe automating some sort of what are the best, in this case, building an automated website that tells you the best restaurants in Boston. I mean, there's a bunch of different applications of a technology like this. So in this particular case, an example of something that it learns is that this is a review of a beer, actually. It learns from this thing, if you read the highlighted sentences here, so the review said very pleasant ruby red amber color, a relatively brilliant finish. So it seems to learn that this review is saying, well, this beer looks good. So some people like their beers to look good, so it looks good, so it gives it 3 stars, okay? And it says a nice blend of caramel and hoppiness found together. So this beer also gets a 2 stars for aroma, okay? So this is an example of the output of this thing. But this model by itself doesn't tell you why it learned this. It just says 3 stars for look and 2 stars for aroma with no input. So a human looking at this might say, well, this red sentence and this green sentence are why it's given this, but the algorithm by itself doesn't give you why. It just gives you the rating, okay? So you want to get why out of it. And what these researchers did is they developed this thing they call this rationale framework. And the idea with rationale is to take any neural network, so not specifically this neural network, but to take any neural network, and they actually learn another neural network from that network that they call the rationale network. And what this rationale network can do is it can, from the base network, you learn this new network that when given an input that would go to the base network, this new network, when it's given that input, gives you a subset of the input that would produce the same answer on the base network as the entire input. Okay, so for example, if it were given this beer review, what this rationale might give out is these 2 sentences. So it would take that entire piece of text and just give you the 2 sentences that were highlighted in color there. And the idea is that these 2 sentences, when fed into the base blue network here, would give exactly the same output as the entire input. Okay? And why is this useful to a user of this? Well, because now I understand what parts of the input were the ones that were actually the important ones that caused the network to learn what it did. So it gives you some confidence that this network is doing something that is sort of intuitively reasonable, right? That we're not in the poodle versus ostrich situation, that we have a network that is actually doing something like we expect. So I think this is an example of a kind of really cool, important research that we can do in this space, and to build systems around these kinds of algorithms that will help people to deploy these sort of black box neural net models in a much more comfortable way. The other project I want to talk about in a little bit more detail is a project we call ModelDB. This is a project I've been doing with some of my students where we've sort of been inspired by the fact that people who are building these machine learning models, so this word model, I've used it a bunch already, hopefully you guys have a little bit of a sense of what it is, but these machine learning models are a model is essentially something that takes, the most typical form of a model would be something that you train it on a bunch of examples, like restaurant reviews and star ratings, and then this would be a so-called supervised model. What the model does is it, given it some input that you haven't trained it on, it can give you a prediction on it. So a model is like the engine. These models are the engines of machine learning. They're the things that take the data and extract the insight out of it. Okay? And they're the way all machine learning essentially involves building and training these models. In a sort of iterative process that looks like this, you have some set of data that you use to train or build the model. Okay? You refine the model over time and add new features to it, and you just do this in a loop. So you build it, you build and train the model, you test and evaluate the model, you see how good it's doing, and then you improve the model. And you do this over and over again until the model gives you good performance on some set of test data that you have. So to give you, an example of what this might look like very concretely, suppose you want to build an algorithm that predicts whether, some people are going to default on a loan. Okay, so what you'd like to do is, given their names and their professions and their credit history or whatever, you'd like to output a risk of default. Okay, so maybe, Barack Obama has a good credit history, has a low risk of default. Lindsay Lohan is, a struggling artist, has a terrible credit history, so maybe she has a high risk of default. And Warren Buffett has, more money than God, and so therefore, he's not going to default, right? So, the kind of thing, just don't worry about the text here, but the kind of thing that you would do is you'd start off, you build some model, which is predicting some default from some collection of some base data. You have some set of features like your bank account balance, your gender, your education, your merit, your age, and then you train a model based on things like a logistic regression model. And the first time you do this, maybe you get 62% accuracy. So you had some test data set that you used to evaluate your model, and said 62%, okay? So then you go back and you make changes. You try new features, you try clean data sets, you try different parameters, you try different models, okay? This is a small example. These kinds of changes are the sorts of things that people would do, not 1 or 2 or 3 iterations of this, but literally hundreds or thousands of iterations of this if you're building a real model on a real complicated data set. Okay, and the problem is that there's no way to sort of manage this process. You go through thousands of these models, you update the models all the time, and there's no standardized way to track the history of this modeling process. And that makes it really difficult to collaborate and reproduce models. It's sort of like, I showed this cartoon, this sort of like the way that people manage their documents out in your own personal documents folder. Probably all of our documents folder looks kind of like this, untitled 4D mom.jpg, mom@rest.jpg. File systems are not a good way to organize your data. People are terrible at, they don't promote, sort of carefully organized data. And this is sort of the state of the art for machine learning. People basically store these models in whatever they store them in, probably different documents sitting in their documents folder. And instead what we'd like to do is to sort of take this from, we'd like to, the idea in ModelDB is basically to build a database system that stores all these models. And this is a problem, this sort of bad organization is a problem because there's no record of experiments, there's no ability to understand what you already learned or already tried, there's no ability to reproduce results, there's no ability to go back and search and see what performed well and what different sets of inputs, and there's no ability for teams to collaborate. So we think this is actually a huge problem, and that's the idea in ModelDB is to build a system to manage the history of these building of models. Okay, so you can think of ModelDB to machine learning as databases are to files of data. Right, so we want to capture these models, store them, and query them. It has a bunch of really cool features. I'm not going to go into the details of it because the details of it look like me showing you a bunch of Python code and walking you through the steps of it. But the details are, I think, pretty important. So it has experiment tracking, so you can log all the models, all the parameters, all the pipelines via an API. It has versioning, so you can have different modeling runs. You can compare those modeling runs to each other. It has reproducibility, so you can go back and rerun any model that you built at any time on any input data set. It has the ability to do comparisons and queries and searches of models, so I can compare yesterday's model to today's model, or Jane's model to Bill's model. And then it has an ability to do collaboration. So it gives a centralized repository of models where people can look and see what's been done in the past, where people can continue work that's been partially completed by another person. It's available, you can go check it out. It's an open source project, and one of these things where I think this isn't a deep or radically complicated idea, but it's one of these things that I feel like is just needed in order for us to move from where we are now, which is this sort of black art of machine learning, to a much more principled scientific approach to using some of these tools to find this. All right, so that kind of wraps up what I wanted to say. I'll just quickly summarize what we're trying to do in systems that learn. We're trying to accelerate and democratize the building of these systems that learn. We're trying to train the next generation of researchers differently, and we're building new algorithms and tools for this emerging area. And I just told you about 2 of them, but I could talk about 30 of these. And this is part of what's cool about being in a place like MIT is there's this huge diversity of things that are going on in this space, and we're trying to kind of take it all together and package it up in a way that really have a lot of impact on the world. So with that, hopefully I have time for a couple more questions. Thanks very much.
We have one question.
One question?
One question.
Okay, I took a few already, so we got one more.
Thank you for your talk.
Sure.
Will we ever get to the point where a normal human who's not
trained in algorithms and machine learning and systems can actually take advantage of the technology and aim it at a corpus and have it learn stuff?
So I think that's a very hard question to answer. Certainly, there are many people who are aspiring to do that, and there are, the challenge is that there's a lot of technical details that you have to understand in order to understand whether this thing is really working well. So these models are working well. I expect that what we'll see is that in some, so we will see examples of this in certain particular domains where you will be able to take, in particular, well, you probably will be able to take models that have previously been trained and apply them to your data to do interesting things. So we're already seeing this with some of these deep networks where you can take a model that's been trained for computer vision and you can apply it on your imagery data set and get pretty good results. And you have to, right now you have to be a competent software engineer to do this, but you don't have to understand the details of the algorithms to do this. And I think we'll see more and more of that. Again, I think a real risk of this is that when you start to do that, you run this risk of, you think this network has been trained to do computer vision because it does a great job of recognizing cats and dogs, but then you start feeding it, pictures of food or something, and it finds cats and dogs in your food, right? So you have to understand the context around these things, what these things were built for, and you also have to understand when they're going to fail and what their limits are. And I feel like that's really a barrier to some of the adoption, and those are the kinds of problems we're trying to get out. But I think we'll get there. People want this. It's not going to, it's not like you're going to be able to go. Of course, there's going to be different levels of expertise, like in engineering, but there will be. It will get better.